Hello, everybody. So last time we um, discussed the Rankine cycle with superheat and reheat, and then we solved this problem. Let me share it. Uh, this problem. Okay. So by the way, I noticed that some of you may be able to solve the problem by drawing the process diagram. Aside from the TS diagram, uh, some of you may benefit from doing the process diagram as well. And that's okay. I encourage you to draw the process diagram as well. For example, for this one, the process diagram is here. Okay, so please feel free to draw the process diagram. And then label the points, uh, inlet and outlet for each of the devices. Label them according to your label on the TS diagram, just like this example. The labels actually match, and that may help you solve the problem better or easier. Okay, let's go back to uh, the problem. Okay, we finished solving this problem. Basically, what we're being asked is the efficiency of this Rankine cycle with superheat and reheat. So just like in our previous problems, we solved for the property at each point or in the inlet or outlet of each device. Okay, but the difference here is that we have a high pressure turbine and a low pressure turbine. Okay. And because of that, our efficiency equation would have to accommodate those two turbines. So we have HB minus HA right here and HD minus HC. So this accounts for the two turbines, and then we also have the work required by the pump. Okay, and don't forget we have to put the for efficiency we need to put absolute value sign. Okay, absolute value sign and multiply by 100. Oops. All right. Okay. And after solving for the efficiency, we also tried solving for the Carnot efficiency of a Carnot cycle operating at the same pressures. So same um, inlet, boiler pressure and exhaust pressure. So we did that by getting the temperatures using the steam table. So imagine a rectangle inside the saturation curve that would represent the Carnot cycle operating at the same pressure. Now we would continue with this problem and we would solve the problem if there's no reheat. So, since our initial solution involves reheating, let's compare it with the same process, but this time there's no reheating. Okay, let's try that. What if there's no reheat? Right. We assume there's no reheat. What will happen to our diagram? If there's no reheat, immediately after entering the high pressure turbine at point at inlet A, point A, it will expand to point D. So instead of RD being here, RD will be somewhere here. Okay. And therefore, assuming isentropic expansion, SD prime will be equal to SA. Okay, kasi wala nang reheat. Okay, so directly it will just be equal to SA. Okay, let's write that. SD prime is just equal to SA, and that value is 6.9013. And then from the steam table, SDL is 0.6493 and SDV is 8.1511. Okay? We solve for x prime by inputting in the equation S D prime. No, 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 no. Yeah, SD prime equal to SDL times 1 minus x prime plus SDV times x prime. So for x prime, we will get 0.833. So what do you notice? Uh, the quality is lower. Okay, the quality is lower because without the reheat, ano ba yung quality? The previous quality is x equal to 0.92595. But what we got without reheat is 0.833 because it expanded to a point that is farther away from the saturated vapor line or curve, saturated vapor curve. So the moisture is higher, quality is lower. Let's proceed. So after getting x prime, what's the next step? We solve for HD prime. Okay, we solve for HD prime. So from the steam table, we get the properties of HDL. HDL is 191.832, okay? And HDV is equal to 2584.8, okay? And then using x prime, we get HD prime, and the value is 2186.13. Let me rewrite that. 2186.13. Okay. Um, Sige, so we got HD prime using the efficiency, given efficiency, right? May turbine efficiency of 80%. Okay, we solve for HD. Uh, so what's the equation? Efficiency equal to delta H over delta H sub S. So for the turbine, efficiency of the turbine, remember, the ideal delta H is below the fraction. So it's the denominator. And so we have this amount. Okay, so we have delta HS, which for the turbine, it's HA. Okay, so uh, let's write that. HD, this is HD minus HA, right? Then HD prime minus HA. Okay, so we know HD prime, HA. We can solve for HD. So I'm just looking for the value of HA. Yep, we have that value. So solving that HD you will get 2473.4452 kilojoules per kilogram. So let's continue. At point E, it's saturated liquid. Saturated liquid. Okay. What is point E? My point E is here. So, it's the inlet of the pump. Pump inlet, diba? Point E. So again, I recommend for you to also draw the process diagram. Aside from the TS diagram, please draw this one as well so that you can identify, maybe it's harder to identify the devices on the TS diagram. So draw the process diagram. So a point E, it's the outlet of the condenser, inlet of the pump. So right here, saturated liquid. So if it's a saturated liquid, we can know based on the pressure. So the outlet, what's the pressure at point E? Diba, it's the PE is equal to PD, okay? PD, without the reheat, and that is given 10 kilopascals. PE is equal to PD equal to, 10 kilopascals. 10,000 pala. Ano ba yung given? Let me check. Yeah, 10 kilopascal. 10 kilopascal. PD equal to 10 kilopascals. Okay. And then from the steam table, so let me rewrite. From the steam table, uh, we can read the properties. HE equal to 191.32. Okay. And then also helpful to get V sub E. V sub E equal to uh 0.001. Kinonvert ko na 0.0010 meter cube per kilogram. Okay. Okay. Next, point F. Let's view point F. What is point F? Okay. Again, from the diagram, point F. So it's the outlet of the pump. Okay. And in our TS diagram, in on our TS diagram, ano siya? Anong state niya sa TS diagram? It's a subcooled. Okay, subcooled liquid. Okay. So exiting the pump, subcooled liquid. Um, the pressure is equal to the high pressure turbine. So PF equal to 10,000 kilopascals. So equal to the high pressure turbine. So we try to calculate for delta H sub S. Okay, the ideal delta H or isentropic delta H. Delta H sub S is equal to, what's the formula for the pump? Remember, we derived this from the fundamental property equation, and that is volume times the delta P. And in this case, diba, our delta P is P sub F minus PE. And then we can get, substituting the value. So meron na tayong V sub E when we have the PE. Delta HS, we get it as 10.09 kilojoules per kilogram. Now, what is our delta H actual? So, for the efficiency of the pump, delta HS nasa taas, delta H nasa baba. Kasi mas maliit si delta HS. Okay? Correct? Um, okay, so solving for delta H actual, so we're expecting this is higher. And we know that efficiency is given, diba, at 0.75. So solving for delta H, just substitute the values, you will get 13.4532. Okay, just substitute the values. Alright. So now we calculate for the end of the cycle without reheat. So this is the end of the cycle. What is our equation? So for the turbine, diba, HD minus HT minus HA, and for the pump, HF minus HE divided by, divided by the boiler. So let me, review natin. So HF minus HE, tama, H. The boiler is HE minus HF. Okay, HE minus HF. So we have everything, all the values of the H that we need. So times 100. And you substitute the values, and you will get 33.235%. Okay? Compared to, wait lang. Just review the H, tama, HT, HF minus H. Oh, yeah. So, dito kasi, by the way, in the with reheat, no, may dalawang step, may dalawang boiling part. That's why in denominator, dalawa. Pero, without the reheat, isa lang. HA minus HF. Okay? So, let's make a table to compare the values. Summary. Let's summarize the summary. So, with the X value, the work net. So, by the way, I'd like you to calculate on your own yung work net, QH or Q in, or let's just put the same yan, Q in the end of the cycle on end cycle. For without reheat, and then with reheat. So without reheat, the X is 0.33. X prime. X prime. Hindi na natin calculate yung X. So let's just look at X prime. So work net, ito, calculate this on your own, but this value is 1135.7968. Q in is calculate this on your own then 3417.4148. The end of the cycle is 33.235%. Okay? With the reheat, our X prime is 0.9259 and our work net is negative 1375.1308. So calculate that on your own. Our Q in is 3846.7988 and our efficiency is 75%. Compared to a Carnot cycle, our Carnot's efficiency is 45.39%. Alright. Okay, so what do we notice? So by the way, when you calculate work net, diba, this is for the turbine. For the reheat, um, two, two times yung expansion niya, so you have to add. And also, for Q in, dalawang times yung Q, yung absorption ng Q, so you have to add. Okay? So, please calculate this. Calculate ba natin? So, let me check. Yeah, we did. For QH or Q in, turbine. Ayan, nakalculate pala natin. Just calculate the one for, without the heat. Okay. So what do we notice? May increase in the end of the cycle. Okay. Although, parang isipin nyo, maliit lang. But, in terms, when we translate that to a large scale, uh, it's significant. Okay, significant, siya, increase in the efficiency when we're talking about large scale operation. Okay? Okay. So now we proceed on to the next topic. Other ways to increase the efficiency of the cycle. Okay. We also have a technique called Rankine cycle with regeneration. So, on the TS diagram, as you will notice, heat is transferred to the working fluid. So, at this step, this part, okay, of the boiler, the temperature is relatively low. So, nandito yung step na yan. So, this is the high temperature, the low temperature. So, because of this, it lowers the average heat addition temperature and thus it lowers the cycle efficiency. To remedy this shortcoming, we have to raise the temperature at this step. And that we call that, okay, the step wherein uh, the liquid leaves the pump. And we call it the feed water heating. Okay, so before entering the boiler here, we try to raise the temperature at this point. So that when it enters the boiler, mataas na yung temperature and thus increasing the cycle efficiency. And that's called the feed water heating. And how do we heat the feed water? So how do we accomplish this? We do this by bleeding the turbine, okay, at various points. So in this steam, which could have produced more work, okay, is used to heat the feed water instead. and we call that in feed water heater or FWH. And the process is called regeneration. What does it look like on the process diagram? Okay. So remember, in our basic Rankine cycle, what happens here after the condenser? Whatever liquid leaves the condenser, it will enter the pump and then it will enter the boiler. But because of the additional step of regeneration, so our goal is to increase the temperature at TG, temperature TG, so before it enters the boiler. And we do this by putting a feed water heater right here. And we heat the feed water using the steam that is uh, ble the steam coming from the turbine by bleeding the turbine. Okay? Yan. So may dalawang pump. Uh, First pump, okay, uh, is the one that is at the exit of the condenser. And then the next pump is at the exit of the feed water heater. What does it look like? And then later pa. Regeneration not only improves cycle efficiency, but it also provides a convenient way of deaerating the feed water. Deaerating means removing the air that leaks in at the condenser. And thus it also prevents the corrosion in the boiler. Okay, so without the air, it also prevents the corrosion. In addition to that, it helps control the large volume flow rate of the steam at the final stages of the turbine. So this is because of the large specific volumes at low pressure. Low pressure. So remember, inside the turbine, expansion happens, and at the exit, we expect a large volume of steam because of the low pressure. And thus, regeneration helps control this large volume. And therefore, this process, Rankine cycle with regeneration, has been used in modern steam power plants since the 1920s. And this is what it looks like on a TS diagram. So this is the feed water heating step. Okay, so the steam, instead of expanding fully from point A to point B, nahati siya. So we have to do a mass balance here. We split the steam. Some of it will go to the feed water heater, while some of it will expand fully. Okay, then like I said, there are two pumps right here. This step and this step. Okay. So we try to solve an example. Okay, for this example, 450 psi a steam is superheated to 900 degrees Fahrenheit before entering a turbine. Steam is extracted for feed water heating at 135 psi a. The steam enters the condenser at 90 degrees Fahrenheit. Determine the expansion efficiency of the turbine if it produces 110,000 kilowatts when the mass flow rate of the steam is 255 pounds per second. And letter B, determine the thermal efficiency of the cycle. Assume negligible pump work. Okay, so let's try to solve the problem. Okay, so let's try to solve the problem. By the way, I will be sharing this image to you, the whiteboard, and I also copy pasted the problem for each of the solution. So don't mind the numbering of the sample problems. I missed some of the numbers. Just don't mind it. So let's try to solve example 7, which is Rankine cycle with regeneration. Okay. So I just, for easy solving, I just copy pasted the process diagram and the TS diagram. So let's write the given. So what's the given here? Okay, we're given at PA, superheated steam. Okay, from the boiler, before entering the turbine, we're given PA equal to 450 psia. Okay, and also TA is given 900 degrees Fahrenheit. So these are the superheated pressure and temperature. And next, we are also given um, PE. Okay. Steam is extracted for feed water heating at 135, diba? So this is at this point where we extract steam for feed water heating. So PE, ito yon, PE, we extract it, and that is equal to 135 psia. Uh, enters the condenser, so that is TB, enters the condenser. This is the condenser, right? So TB equal to um, 90 degrees Fahrenheit. Okay, so much better if you also draw the process diagram with the TS diagram. But just make sure that your labels are correct. Okay. And then the required values. So these are the given. A is the efficiency of the turbine. Efficiency of the turbine. And B is the end of the cycle. Okay. So, and we can assume that there's negligible pump work. So what is the equation of the efficiency of the turbine? Um, so we're also given pala, I forgot. We're also given the actual work of the turbine. Work by the turbine work shaft is 110,000 kilowatts. So we can write the efficiency of the turbine as the ratio between the actual work. So don't be confused sa work shaft. Dito yung work isentropic. Okay, so let's para hindi malito lagay isentropic or teka. Yan, work isentropic. So work shaft, the actual work over work isentropic. So that's the equation of the efficiency of the turbine. So for the efficiency of the cycle, we can compute it by adding using the isentropic H delta H values, right? For the turbine and for the QH. So we can write the equation HB minus HE erase. We'll just use the given actual work. Okay. So remember, we also have that equation for the efficiency of thermal efficiency of the cycle. Teka, let me go back to the equation. This one. So let's just use the actual work kasi given na tayo na actual work for this problem. So we only need to find QH. Okay? So this is for the negligible pump work. So let's just use the equation for that. Work shaft over QH. Okay? So what's the next step? We try to find the properties of the steam at each point. Let's start at point A. Point A where superheating happens. So it's a superheated vapor at point A or superheated steam. From the steam table, HA equal to 1468.3 BTU per pound mass. Okay, and SA is 1.7115 BTU per pound mass Rankine. Okay, once ko na susulat yung unit. Later, kayo na magsulat ng unit. And then at point B, it's wet steam. So it's fully expanded. Okay, at point B. Point B, so full expansion from the turbine and it at the inlet of the condenser. It's wet steam. From the steam table, we know the PB is given, right? TB is given 90 degrees Fahrenheit. Okay. So we try to read the values of HBL and HBV. HBL is, so from the steam table, HBL is 58.02 BTU per pound mass and HBV is 1100.08 BTU per pound mass. We also tried to read the properties for entropy. SBL is 0.1115 BTU per pound mass Rankine. SBV is 2.0086. Okay? So if we consider isentropic expansion, SB prime equal to SA. If you consider isentropic expansion, diba? This is vertical line right here. And then that is equal to 1.7115. Okay. So we solve for x prime. We solve for x prime. Hindi ko nasusulat yung equation. X prime is 0.8434. And then solve for HB prime using that x prime. You will substitute the values. You will get 937.5. Okay. Isentropic. So this is assuming isentropic expansion. How about point E? Point E is the, so right here we bled out the turbine, it's still superheated vapor. Okay, still superheated vapor, point E, right? Okay, so this is for the feed water heater. You're using it for to heat the feed water heater. Superheated vapor. Or superheated steam. Superheated steam para hindi confusing. Superheated steam. What do we know? Given PE, diba? PE is 135 psia. We assume isentropic expansion. So SA is equal to SE prime, or SE prime equal to SA equal to 1.7115. Okay, and then from the steam table, you have to interpolate from the steam table. Okay, interpolate using the S value and the using the S value, you can get the H value. Okay, so pakita ko na lang din how to interpolate using the S value. So here we have SE prime, hanapin, find in the steam table under the pressure 135 S 135 psia. You will get like this two, in between of these two S or two entropy. Ayan. Kasi we just know one property eh. Diba? So we don't know the it's superheated, so don't know the temperature. So we use SE prime. Okay, so SE prime is 1.7115. Okay? Using that, interpolate the value of HE prime. Okay, and you will get, okay, so this is the unknown right here. 1327.2. 1327.2. You will get HE prime by interpolation from the steam table using the pressure and entropy. And assuming isentropic expansion, so HE prime, you will get 1314.68. At point C, it's saturated liquid. Okay, saturated liquid. And what do we know? TB equal to TC equal to 90 degrees Fahrenheit. Okay, why? Again, so let's TB equal to TC, and that TB is given 90 degrees Fahrenheit. Okay. Um, so point C. From the steam table, we know that PC or P saturation at that temperature is 0.6981. Remember, we're dealing with saturated liquid, PSIA. Okay. And we also read helpful values. HC for, this is for the liquid part. Okay, HC equal to HL, the liquid part, 58, 58.02 BTU per pound mass. Okay, HL to add the liquid part of the saturated properties. And we also read VC, which is 0.01610 feet cube per pound. Okay, feet cube per pound. Okay, let's go to point F. Point Wait lang. C na tayo. So, YF. Okay. Kasi we can know this since this is on the saturated liquid curve. So what do we know about point F? That its pressure is equal to PE, which is given 135. So let's jump to this point because we can easily know the properties at point F. PE equal to PF, diba? It's on the same saturated curve, a saturated line. What do we know at point F? PF equal to PE equal to 135 PSIA. Okay? And we can read from the steam table. We read from the steam table yung properties ng saturated liquid na yan. Okay, so HF. So just read the saturated liquid properties, and that's 322. HF is equal to 322 BTU per pound mass. And also read uh, the VF, 0.018 feet cube per pound. Feet cube per pound. Now we consider the first pump. So we consider the first pump. Okay. Consider pump 1. So let's draw the pump. So there's done on the pump. So for the first pump, ang inlet niya ay HC, outlet niya ay HD. Balikan natin ha, first pump. Ito yun. Okay, inlet niya ay first pump HC, HD. Okay, so ito siya. So remember, our delta H sub S of the pump is equal to V delta P. Okay, so it's VC times delta P, which is PD minus PC. PD minus PC. So we try to solve for, and this is equal to HD minus HC. Okay. So we try to solve for HD by plugging in all the values. Okay. We plug in all the values. Okay, so kayo na yung mag-rearrange ng equation. I just input here yung final value. So meron dyang dimensional analysis. Sige, ilagay ko na nga lang din. HC, yung nakuha natin sa taas. So, by the way, we're dealing with okay, so 58.02 BTU per pound. So, by the way, HD prime to. We're dealing with isentropic expansion. Kasi itong equation na to is for isentropic BTU per pound mass. Okay. Plus VC, so that's 4 as 0.01610 feet cube per pound. Okay. Times 135, that's PD minus PC. Diba? So, this is, anong unit ng PSI? Pound force per inch square, diba? That's PSI, pressure. So, we convert to BTU. How? So, we multiply by, okay, we convert yung inch squared to feet squared. And then, we can use this conversion factor. 1 BTU is, it depends on you kung paano nyo gusto i-convert to BTU per pound mass. Ito, pound mass. Okay. BTU, 778 feet per pound force. Let's see. Magka-cancel to. Ano pa magka-cancel? Ito, feet, feet cube. Yan, magka-cancel yan. So, dapat magiging BTU per pound mass to. Magka-cancel ba to? Pound for PSI. Pati nag-cancel. Mali pala yung label ko dito. Foot pound force, hindi foot over pound force. Foot pound force to. Foot pound force. Okay, so, yan. So, yan, magka-cancel na. The ending is BTU per pound. So, it matches, ito, pound mas yan. It matches the first term. Okay? So, HD prime is equal to 58.42 BTU per pound mass. So we consider the feed water heater. Next, we consider the feed water heater. So, saan siya? Saan siyang step? Ito, feed water heater. We do a mass balance here. Ito yung entry to the feed water heater. Okay. Consider the feed water heater. Let's draw that. Let's draw the feed water heater. So, ano yung pumapasok sa feed water heater? Dalawa. So, yung this is from the turbine, HE prime. And then we also have from the condenser, HD, papasok sa pump, HF. Okay, so check nyo. Check ko. Tama. Okay. So, ang mangyayari kasi dyan, remember, if may fraction na let M1 be the mass fraction of the steam entering the mass fraction of the steam from the at HD pala. Mass fraction of the steam at HD. Okay. So, kung M1 to HD, this, itong, ano na to, should be 1 minus M1. Gets? Okay. So, di ba, whatever enters the feed water heater, let's assume na, that's one whole. So, if we express as mass fraction and we let this, inlet D as mass fraction M1, so this should be 1 minus M1. Okay. So, let's write that mass fraction at B. So, this one is 1 minus M1. Okay? So, our goal here is to solve for M1. If we make a mass balance, ano yung, energy balance pala, energy balance around the feed water heater. Okay. So assuming there's no kinetic energy, potential energy, there's no work done, it's just simply mixing. So remember, so delta H is just 0. So if we write it, it's HF times 1, okay, times 1, di ba? Minus 1 minus M sub 1 times HE prime minus M1 times HD. So by the way, this is also HD prime. Okay. Equal to 0. So it's an energy balance around the feed water heater. Substituting the values, we have HF, we have HE prime sa taas, HD prime. We can solve for M1, and M1 is 0.79. Therefore, 1 minus M1 is 0.21. Okay. So, the reason why we did that is, remember, we want to know the mass of the steam that was extracted, okay, at this point. And whatever is left, okay, went to do a full expansion in the turbine. So, yeah, nag-split kasi siya dito. So, we want to know the splitting, the ratio of the splitting. Now, we consider the turbine. Consider the turbine. The turbine, okay. So, ano yung mga, pumapasok sa lang, which is yung HA. HA. And then, meron siyang work shaft. Work shaft. And then, okay, let's assume isentropic expansion first. And then, diba, remember, na-split siya. This is HE prime and then HB prime. Na-split siya. Okay. Turbine ba? HA, work shaft, HE prime, HB prime. Na-split siya. So, and this mass fraction, na-solve natin yan sa taas. 1 minus M1, di ba? 1 minus M1. And then, ito yung pupunta sa condenser M1. So, we know the values already for HE prime and HB prime. HB prime. So, assume isentropic expansion first. Okay? For simplicity. we can solve for the isentropic expansion, isentropic work. Okay, expansion. So we do an energy balance around the turbine. By doing an energy balance around the turbine, assuming isentropic expansion, so we're writing, okay, HE prime 1 minus M1. So this is uh our energy balance is just delta H equal to work shaft. Okay. And we have to consider the mass fraction for the H values, HB prime times M1 minus HA times 1. Okay, nagets ba? So this is delta H equal to work shaft. So that's the energy balance around the turbine. So we know all of these values, lahat na except to. So we don't know this, and that's what we're solving for. Just substitute the values, and you will get negative 451.59 BTU per pound mass. So now we can solve for the efficiency of the turbine. Okay, so remember this is the work shaft actual over the work shaft isentropic. This value is given. So just substitute these values. So remember, negative yan. Okay, yung given na work shaft actual. I just forgot to put the negative sign in the given, but you should know that it's negative. Okay, negative. Divided by yung 459 BTU per pound. And then we're given the mass of flowing stream given sa problem. But I forgot to write it in the given. Ayan na, mass of flowing stream. So let's write it. Given the mass of flowing stream is 255 pounds per second. Ay, 255 pounds per second. Kasi, ang mapapansin nyo, yung ano natin, ilalim natin is BTU per pound, pero our numerator is kilojoules per second. So, you need the mass flowing stream, the mass flow rate. So, I leave you to convert this. This is 255 pound per second. Sige na, convert na 60 seconds per minute. Na depende din kasi sa sa gusto nyong conversion factor. Ang ginamit ko, 1 kilowatt is 56.8699 BTU per minute. So, it depends kung anong conversion factor meron kayo. So, times 100, the end of the cycle, the turbine pa lang to, 90.54%. Haba ng problem. My gosh. So, this is the answer for letter A. Okay? Nung napansin nyo, sinolve lang natin yung HE prime assuming isentropic expansion. Kasi gusto natin malaman lang yung isentropic expansion. So, I mean, sa isentropic pump, isentropic turbine. Okay. Now, we move to calculating the thermal efficiency. Letter B. So, consider pump 2. Consider pump 2. Okay. So, kasi buong, ano na to buong efficiency ng cycle. Kanina, pump 1 lang. We need to know kasi yung HE. Okay. So now, we're dealing with the cycle. Let's consider pump 2. So, may work in or work done on the pump. Ang pumapasok sa pump 2 ay HF. Ang lumalabas ay HG. Okay. Saturated liquid siya at this point, HF. We can read sa steam table. Nabasa na natin yung point F kanina. Okay. So, from the steam table, HF is 322. VF is 0.0180 feet cube per pound. PF given. HG naman is 400. We know PG na 450 PSIA. Okay. Kasi yan ay yung sa condenser. What can we solve is the delta H is around delta HS around the pump, and that is VF times delta P na HG minus HF. So, we want to know ang unknown dyan, yung HG. Ayan. So, meron na tayong VF, HF. And this is, oops, mali. This is PG, V delta P. PG minus PF. And this is equal to HG minus HF. Diba? Outlet minus inlet. And these are known values. Ito yung unknown. Okay. So, plugging in everything to the equation, doing dimensional analysis. Okay, kayo nang bahala. HG is 323.05 BTU per pound. So, may dimensional analysis dyan. Next, we can consider the boiler. Consider the boiler. The boiler ano ba yung pumapasok sa boiler? Hindi ko na kailangan mag-drawing. Simple, ano lang. Isang inlet, isang outlet lang. Yan, Q equal to delta H. That's the energy balance of the boiler. So, QH is equal to delta H equal to HA minus HG. Okay. So, meron na tayong HA na value and HG from, so by the way, this is HG prime. HG prime. Kasi ang ginamit nating equation ay this one is for delta HS. So we can simply just plug in the values. and we will get QH or Q in. Okay. So we need yung mass of flowing stream dito. Mass of flowing stream. Kasi we can, ano na siya, we need the QH na ano, in terms of per second or in terms of na rate siya, hindi per pound mass. Okay. And we can also convert this value to kilowatts na. Okay, so we can solve for the thermal efficiency. Okay, so I'll leave it to you to plug in the values and do the dimensional analysis. So QH you will get here is 38,122 kilo 0.46 kilowatts. Therefore, our end of the cycle, our thermal efficiency is work shaft actual over QH. Just substitute the values times 100 equal to 35.70%, assuming negligible pump work. Okay? So you may be wondering, okay lang bang nag-assume lang tayo ng HD prime at HG prime? So, bakit hindi actual? Unang-una, we're not given the pump efficiency. So, hindi natin talaga masosolve yung actual. And, na sinabi naman na negligible pump work. So, yung difference ng HG tsaka HG prime at difference ng HD at HD prime, something na we can also consider na negligible. Okay, so let's end the discussion here. For this is now the end of the video. Thank you very much.